Welcome to NASA Ames Research Center at Moffett Field, California. We're here today to announce new discoveries from NASA's Kepler mission, which is managed right here at NASA Ames. Getting us started with a few opening remarks is Center Director, Dr. Pete Worden. Dr. Worden.
Thank you, Michelle. Just as an opening introduction, this is really cool. And I'd like to welcome all of you to NASA Ames Research Center here in Silicon Valley. And just like the companies that surround us and the universities, this region has always been known for innovative, different, and groundbreaking approaches. Nothing represents that better than Kepler. Now, I'm an astronomer, or used to be, before I became a bureaucrat. But sometime in the last century, I was in graduate school. And the thing that inspired me was the idea that we might someday find planets around other stars. And at that time, we know of none. And I was hoping that sometime, maybe before I went on to my final reward, that we would find planets. But it was kind of an iffy proposition. Decade or two later, I heard one of the guys you're going to hear today, William Barucki, talk about a concept. And I and some of my colleagues said, that'll never work. NASA said the same thing, but they thought it just might work. So Bill was given a little bit of money, and it actually got turned down, I think, 4 times until it finally got selected. And Kepler, as we know it today, has been an unbelievably phenomenal scientific instrument. It has confirmed more than 115 planets, and it has over 2,700 planet candidates. Its success resulted in it being extended an additional 4 years through 2016. And this has also brought us here to discuss some of the key results we have today. Now, I'd like to say that, just probably in closing this brief introduction, that Kepler represents the spirit and ingenuity of this center, Silicon Valley, California, NASA, and most importantly, the United States. I know of no better way to kind of say that all of us still have the right stuff. So I want to congratulate the team. Looking forward to hearing what they have to say. And I want to turn it back to Michelle. So Godspeed Kepler, Godspeed NASA.
Right. Thank you, Dr. Worden. It's now my distinct pleasure to introduce our panel today. So joining us live via video teleconference from NASA headquarters is Paul Hertz, Astrophysics Director at NASA headquarters. And joining us live here at NASA Ames, we have Roger Hunter, Kepler Project Manager here at NASA Ames. We have William Barucki, Kepler's Principal Science Investigator, also at NASA Ames. And we have Thomas Barkley, Kepler Scientist at the Bay Area Environmental Research Institute in Sonoma, California. And we also have Lisa Keltnager, Research Group Leader at the Max Planck Institute of Astronomy and Research Associate at Harvard-Smithsonian Center for Astrophysics at Cambridge, Massachusetts. We're going to start with opening remarks and then take questions here at Ames. And then we're going to have questions from our panelists, from our participants on the teleconference. And then we're also going to take questions from those on social media. So if you are interested in asking a question, please tweet or post your question with hashtag AskNASA. And those joining on the phone bridge, if you'd like to ask a question, push *#. So with that, let's turn it over to Paul.
Thanks very much, Michelle. I'm Paul Hertz. I'm the Director of Astrophysics at NASA headquarters in Washington, D.C. Excuse me. So NASA astrophysics mission is to unravel the mysteries of the universe, to help understand how the universe began and evolved, and to search for and study planets around other stars. And like Dr. Warden, I remember when none had been discovered. I used to be an astronomer before I became a bureaucrat, and now it's one of our prime missions. The Kepler Space Telescope is one of 12 satellites that we have operating right now, and it's the only one that's capable of discovering and studying Earth-sized planets around other stars. It's not going to be the last such satellite. NASA has recently announced the selection of a follow-on mission called the Transiting Exoplanet Survey Satellite, or TESS, which will launch around 2017 and will discover planets around the stars nearest to our own sun. But today's announcement is about a Kepler discovery, one which takes us on the path towards understanding how many planets there are around other stars, and whether they are small enough to be rocky, and whether any of them might be habitable and have liquid water on them. This is a gradual path that Kepler has been taking us down, and today's exciting announcement takes us even closer to that goal of finding habitable planets around other stars. So with that, I'm going to pass it back over to Roger Hunter, the Kepler project manager there at Ames Research Center.
Thank you, Paul. We're counting on you bureaucrats to get us astronomers more money. And so we have some really juicy information to talk about today. And it's my job to set the stage with a preamble. And if you go to my first chart, I want to talk just a little bit about the scientific objectives of Kepler. We've always wanted to know how rare or how common are planets like the Earth in the galaxy. We want to know what percentage of stars in the galaxy harbor potential habitable planets. If you go to my next chart, I want to talk about the results that we've experienced so far. 3 months ago, the Kepler mission showed this chart to the public. And as you can see, we have already identified, within just the first 22 months of this mission, 2,740 planet candidates. One thing to take away from this chart also is this: there are a lot of plentiful small planets out there, and that is key. We have 16 quarters of observations in the bank, and this is just from the first 22 months. Let's go to my next chart. Let's do a quick refresher on how this system works. Kepler detects planets by transit photometry. If you were standing on the edge of our solar system and looking in, you'd see the Earth do this once a year. And we're using the same concept as we're looking at stars thousands of light years from us. And when that planet crosses the face of that star, we can measure the change in brightness so precisely that we can give you 3 vital pieces of information about that planet. How big is it? What is its orbital period? And what is the distance from its star? Those are key in determining whether a planet is in the habitable zone or not. Now, until today, Kepler had announced only 2 other planets in the habitable zone, Kepler-62b and Kepler-47c, and both of them were relatively large. 22b was 2.4 times the size of Earth, and 49c was even bigger, almost 5 times the size of Earth. But what we're going to talk to you about today are 2 planetary systems. One harbors 2 habitable zone planets, and the other harbors another one that is right on the cusp of the habitable zone, and these are smaller planets. I'm going to turn this over to Bill Barucki to announce the first discoveries.
Thank you, Roger. Kepler is certainly making excellent progress toward the goals that Roger enunciated so clearly. And so today, could I have the next figure, please? Today I'd like to announce these 2 planets, somewhat larger than the Earth, in the habitable zone of a single star. The planet in the center there is a little bit bigger than the Earth, 1.4 times the size of the Earth. The other one's 1.6 times the size of the Earth. We think there's a good chance that the center one there might be, in fact, a rocky planet. And in fact, these 2 planets are our best candidates for planets that might be habitable, not just in the habitable zone. They're part of a planetary system of 5 planets that we've discovered so far, but these are the 2 that are most important and the ones that we'll discuss at length. Could I have the next figure? When we talk about the habitable zone, we really need to understand what we're trying to portray here, and that is we could imagine taking a planet and putting it close to a star. If it's so close, in that red region, for example, that it's too hot, the oceans boil. If, on the other hand, we move the planet too far away into that blue region, it's too cold. The oceans would be frozen solid. In neither case do we think that's conducive to the evolution of life. In the middle, between the fire and the ice, is this green zone, the habitable zone, where a planet at that distance around its star could have liquid water on its surface. That habitable zone, shown in green, is a function of the star. How big is the star? How hot is the star? And you can see for the hottest stars, it's quite far out. It gets smaller toward sun-like stars and even smaller toward cooler stars. The star for Kepler-62 is actually a little bit cooler and smaller than the sun. Could I have the next figure, please? Roger talked about two large planets, and they're shown here. The vertical axis is the size of the planet relative to the size of the Earth. The horizontal axis is its orbital period. Earth is in the lower right-hand corner, and that's there for reference. Roger mentioned the two upper ones. We're interested in the two lower ones. That's Kepler-62e, orbital period of about 122 days. Kepler-62f, orbital period of about 267 days, getting close to the orbital period of the Earth. Next figure, please. This is an animation. We can see us start flying through past the two outer planets, and then we come to the inner planets. There are three inner planets, one of which is the size of Mars. We look at the star itself. That star is 2/3 the size of the Sun. It's about 1/5 as luminous as the Sun, but it's older than the Sun. It's about 7 billion years old, so it and its planets are older than our Sun, older than our planets. It's about 1,200 light years away, so it's not all that close. Here we can see the planets in the habitable zone, and we're moving towards this planet that we believe is warm. It may be a water planet, and so it will be hot, warm, and have lots of water. And in fact, if you look at the backside, it might very well have lightning. The next planet that's showing up is 62F, the one that we think may very well be a rocky planet. It's much cooler. It's got polar caps. Now we're surmising this. Polar caps, we think that it may have significant land masses and certainly the possibility of water as well. The three inner planets and the two outer planets are part of this 5-planet system. But we don't know that we've found all the planets. It may very well be that as we continue to look, we'll find planets that are much further out. I don't know whether it'll be Jupiter's or whatever, but we're continuing to look for these other planets as well. Next figure, please. Here's our comparison of the Kepler-62 planetary system and our solar system. There's some similarities, there's some differences. Certainly the habitable zone is quite a bit smaller than that of the solar system. So that's a difference. But there's similarities. If we look at the three inner planets for Kepler-62, they're also close to their star. They're very, very hot. Some of them might have liquid zinc on the surface, hot enough to have liquid cadmium on others. So they're very hot. And that's very much like Mercury and Venus. If we look, there's two planets in the habitable zone of the solar system, Earth and Mars, and two in this system, 62E and F. 62E is somewhat bigger. We think might be a water world, but we don't really know. We have not been able to measure the masses of these objects. That's something we would hope to do someday in the future, but right now we are telling you what we know and what we think is a reasonable understanding of what these planets are like. Could I have the next figure, please? When I talk about the fact that we think these two planets might be rocky or a rocky and a water world, what evidence do we have for that? What can we surmise? And so again, we have a graph here. The size relative to the Earth on the vertical axis. The horizontal axis is the orbital period, and again, the Earth's there for reference. But these aren't planets just in the habitable zone. If you look to the left, there are three planets, Corot 7b, Kepler-36b, and Kepler-10b. These are planets that are small, in fact, the same size as Kepler-62f, but they're very close to their star. They move very rapidly, and that means with radial velocity, we can have people like our colleagues like Jeff Marcy go to the Keck telescope and measure their masses, and we get densities. We know these are rocky. We have measured their densities, and they are the same size as Kepler-62f. So we surmise 62f is also rocky. That would be consistent with theory. And we note that we have never found a gas planet anywhere near that small. So we think 62f has got a good chance of being a rocky planet. 62e is a little bit bigger. It might be rocky. It might be a water world. We don't know. And in fact, it might if it represents a water world, it's a planet like we don't have in our own solar system. So it's sort of a mystery planet. But the summary of this is we have found 2 planets that in the habitable zone of another star, and they are the best candidates found to date for habitable planets. Now at this point, I'd like to introduce Tom Barclay, who will tell you about another planetary system that Kepler has discovered.
Thanks, Bill. So I think we're seeing very nicely as Kepler goes along, we're finding these small planets on longer and longer orbital periods, pushing towards finding these small planets in the habitable zone. Move on to the next slide. So Bill's star is about 1/5 as luminous as the sun. We probably wouldn't consider it a sun-like star. The purpose of the Kepler mission is to find small planets orbiting sun-like stars. That's very different to Bill's system. Today I'm announcing a super-Earth-sized planet. That's a planet about 1.7 times the size of Earth, orbiting within or close by to the habitable zone of a star very much like our sun. Next slide, please. I want to take you back now to January of this year. We announced the new Kepler Planet Catalogue. These are our new planet candidates. They're not confirmed, but they look like planets from what we understood at the time. This plot here shows the size of the planet on the vertical axis and our best guess at a temperature on the horizontal. The green region is the habitable zone, what we defined as a project as a habitable zone. The 4 yellow dots show 4 new, potentially rocky, super-Earth-sized candidates. And we were really excited by one of these candidates. We catalogued it as KOI 172.02. We were excited because it was orbiting a sun-like star near to the habitable zone. Today, we can announce what we've confirmed that this is a bona fide planet. This is a real planet orbiting this star, Kepler-69. Here we show a schematic of the habitable zone. If you compare it to what Bill showed earlier, the habitable zone is much further out. That's the green region. And these showing the solar system compared to our system to scale. It's very similar size to the habitable zone of our own star. We see our planets here. There are 2 planets in the Kepler-69 system. 69b orbits very close to its star. It goes around every 13 days and is about 2.4 times as big as Earth. It's very unlikely to have a rocky surface, and it's going to be a hot world. What we're very excited by is Kepler-69c. Here we see it orbiting close to the inner edge of the habitable zone. So as Bill so eloquently said, the habitable zone is a region between fire and ice. Well, this is orbiting closer to the fire than the ice. We consider this perhaps to be more of a super Venus than a super Earth, perhaps. We're not entirely clear of where the habitable zone is. It's an ongoing research area. Move on to the next. So I want to show you here the progression we're making as a project. 16 months ago, we announced the discovery of Kepler-62b. That was 2.4 times as big as Earth. We now consider this a sub-Neptune size, a mini-Neptune-sized planet, because it's unlikely to be like the terrestrial planets of our own solar system, Venus, Earth, and Mars. Today, we're announcing the discovery of 3 super-Earth-sized planets. These are planets that may be rocky, may have liquid water at the surfaces. Below about 1.5 Earth radius, we're more likely to have a rocky surface. This is Kepler-62f. As we move larger in size, we're getting more mass in the planet. We're able to hold more lighter elements, lighter molecules. And so you're likely to possibly have liquid water at the surface, perhaps. We're not too clear. And the reason we're not clear about what makes up these planets is we don't have anything like this in our own solar system. We don't know the mass, so we have to go to models and theory to try and understand what's going on. So we see here our progression towards this Earth-sized planet. However, we're not quite there yet. You see, none of these are quite Earth-sized, but we're pushing towards it with our announcement today of 3 super Earth-sized planets in the habitable zone. Thank you. I'll pass on to Lisa Kaltenegger now.
So as Bill and Tom told you, it's like we're having, for the first time, planets that are below 2 Earth radii. What we usually use as a cutoff for a solid planet. And then 1.5 we use as a cutoff from the models for a rocky planet. So somewhere between 1.5 and 2, what you're getting is more and more water in these models. So as I agree with Phil, this fascinating idea is that maybe we've actually found the first ocean planets, the first water worlds out there. And what it just shows you is the diversity that we're discovering out there. And let me say that we only have the radius, so what we infer from the models is very exciting, but always has to be taken a little bit with a grain of salt. Could I have the next slide, please? So this is what we already showed you. And here what I want to also point out, you see on the left 69C, then you have the smaller one, 62E, and then 62F. And it's also the same progression, so the Earth is here as a reference. It's the same progression for the flux that they're getting, for the heat that they're getting from their own star compared to our own sun. Next slide, please. And so what we usually do is we actually show you this in terms of a habitable zone. And you see the shaded blue region, and you see the systems that we just announced. So the lower system, so the sun is a bit cooler, 62 is a bit cooler than our own sun. 69 is roughly, well, warmer, not like our sun, but a bit cooler than our sun. But you see that for 62, both of the planets lie in what we call the habitable zone. And one lies smack in the middle of where all our atmospheric models actually say if this is a rock, if it's like Earth, geologically active, so it can actually bump CO2 in the atmosphere, take it back out, then it has or it can have a temperature on the surface that we do. Again, we don't know that, but it is a possibility. And also 62F as 62E, sorry, the closer in one that Bill talked about. So this one is also in the habitable zone. So we have 2 shaded regions here that you see. One is the narrow habitable zone based on our atmospheric models where we put everything in that we know from the Earth. And we know that we have a couple of things missing. This is why we call it the narrow habitable zone, the bright blue region. Because, for example, cloud feedback is something that we don't have in there. We don't know how to do that yet for extrasolar planet atmospheres because it's a very complicated problem. But if you actually heat up a planet, you have more water in its atmosphere, so you should have more clouds. And that basically puts 62E also in the temperature range of liquid water on the surface. And as Bill said, it might be that we're actually looking at one of the first water worlds out there. And so what you see in this graphic is our own solar system on the top. Then you see for reference Kepler-62b. As we say, it's actually a mini Neptune because it's too big. And then for reference, you see 69, where both of the planets are not within the habitable zone, but the error bars for 69c are actually big enough that if we get really, really lucky and the star is actually cooler than we think, then it could be on this border to the habitable zone. So right now it looks like a super Venus, but if all the error bars pan out in the right direction, it might just be at the Venus border and maybe a little bit inside. But the other 2 planets that you see in the lower part in the 62 system is what has got us so excited and me very excited to work on this project. So next slide, please. What we of course want to show you here is what is special or why are we so excited about these planets? Here you see 3 gray circles, and those show you the confirmed radio velocity planets. So you probably heard a lot about the first habitable planets and so on and so forth. And so we show them for reference, and you see that they all fall in the habitable zone. And for those, we know the mass. And it's also very exciting because they could be rocks or they could be mini Neptunes. But they have a potential that they could be rocks. But for this new system, 62E and F, the radius tells us that they're actually solid, what makes it, for me, very fascinating candidates and the best candidates in the habitable zone. Could I have the next slide, please? So here we just shade everything out that you know for reference, and we just show you the beautiful new discoveries. And what you really want is you really want to collect the light from these planets to figure out, to take the data, not just infer whether or not there's water and even signs of life on these planets. And as Paul said, we just got a mission approved called TESS that will look for such planets around the closest stars to us. Because, as Bill said, this is 1,200 light years away, so we'd have to build a huge telescope, much bigger than JWST, to actually read the data in the fingerprint of that planet to figure out if they're really water worlds or not. And if I can have the next slide. Next slide. Here, what I just want to give you a flavor of is all the candidates we have already with the Kepler mission. So you see the confirmed ones at this really pretty images, but you see all the other ones that we're very excited of, that we're still confirming, the green ones, are actually smaller than, so you see the small dots here. These are the ones that we're really excited of in the habitable zone. It just shows you what variety and what is coming up. They're only candidates, not confirmed yet, but this is coming up. So we are on the verge of the discovery of so many very exciting planets that in turn will tell us so much more about how rocky planets work, how they can be diverse, and we will then learn something as well for our own Earth. That's why we're also doing that. We want to, if we can, have a look in the future of our own Earth and learn from all these planets out there how rocky worlds work in the first place. And so if I can go to the last slide, here I would like to just speculate, and that's what we're doing. We have the radius of these two planets in the 62 system. And what I find beautiful, and Bill mentioned it already, we have two planets in our solar system that are in this habitable zone, but Mars is too small. It doesn't have enough gravity to keep holding on to an atmosphere that could heat it, that has enough greenhouse gas. But F, that would also have to build up a lot of greenhouse gas to keep warm because it's further out than we are from the, it's not further out, but in terms of flux, how much radiation it gets from its star, it's further out than we are. So it would have to build up a lot of CO2 to be habitable. And E basically gets a little bit more flux than we do, so you want it to be cloudy just to reflect a bit more flux out into space and keep nice and warm. But this is an artist's impression of potentially, just one interpretation of these planets. And think about it, these planets get as close to each other as Venus does at its closest approximation to us, and they're bigger. So that would be amazing, beautiful jewel up there in the sky if you could be on that planet looking up. And so I just want to leave you with this artist impression again, saying that we have not had a look at the atmosphere. We can't right now. We need closer by planets to do that. But from the radius, we know, or we infer, that it's actually solid planets. We don't have a better explanation. It's very hard to make these gas when they're small. And so for the first time, we found a system where potentially you could have even one more habitable planet, and that's of course potentially, than in our own world. Thank you very much.
Fantastic. Thank you all. We'll now move to questions here at NASA Ames, followed by those participating on the phone bridge. Those on the phone, please press *1 to get, if you'd like to ask a question and get into the queue. And then again, we'll also take questions via social media. So you can tweet or post your question with #AskNASA. So for those in the auditorium, please raise your hand and a mic runner will come to you. If you could please stand, state your name and your affiliation.
Hi, my name's Adam Becker. I'm a reporter with New Scientist. I have a few questions. So first of all, I don't think I caught, how far away is Kepler-69?
It's about 2,000 light years.
2,000 light years. Okay. And is there any reason to think that there's something special about sun-like stars? Is there, I mean, and I guess this is really for all of you. I mean, is there a world in the habitable zone of a dimmer star like Kepler-62 could still have liquid water on it? So is there something special about Earth-like planets around Sun-like stars as opposed to Earth-like planets around dimmer stars?
Can I maybe take that? So what we're basing our information or our models on is the Earth. And then if you change the sunlight, well, it might get a little bit redder, but our atmospheric models account for that. So if the star gets smaller, there is no reason to believe that you couldn't have water, that you couldn't have signatures for life or like conditions for life. On the other hand, what you do have to say, if you're super conservative, is that the one case for life that we have is the Earth. So a lot of people, or some people, would like to have the exact Earth analog around the exact Sun analog. But I would personally say chances that it has the same amount of water or continents, so some people want to have exactly the same mix. We don't think that's necessary because think of the Earth just generally. It changed through its lifetime. It was habitable for all of the time. And just because your star is colder, as long as you're closer in, like with a bonfire, smaller fire, you want to stand closer to be warm. Hotter fire, you want to be further away to be warm. I see no reason why there would be anything special about a Sun analog star. All the stars are Sun-like. But again, if you want to be the person that says, I don't believe life could have gone any other way, needs exactly the Sun, exactly the Earth, you have so far some argument because we haven't found signatures of life on other planets. We don't think you're right, but we cannot prove you're wrong.
Tom, did you have anything to add to that?
Well, very simply, all I was going to say is the one planet we know of with life orbits a Sun-like star. And that seemed natural to be the first place to study in detail would be these Sun-like stars.
Mm-hmm. The other thing I could mention is that when you think about being on 62F and looking out at that star, it would look about the same as our star, except it'd be bigger. But the luminosity, or the light that you were experiencing, the illumination level, would be like if you were walking around on Earth on a cloudy day. It drops by a factor of 5, like on a cloudy day. So it's not too obvious that you could tell the difference if you were on that planet.
Adam, you had another question?
I have several other questions if I can ask them.
All right, we'll see how it goes.
Okay. So, is there a simple way to explain why we think that these worlds that are, slightly larger than Earth could be water worlds as opposed to worlds with a mix of water and land on them like Earth?
I don't know. Can I? Sorry. It falls into my jurisdiction, sorry. The idea is just if you take a planet like the Earth, keep the water mass fraction the same, just make the mass bigger, the volume, mass and volume. So basically what you get is you get enough water that you can cover the whole surface just because you make it 4 times as massive as the Earth, right, according to the radius, but the radius doesn't go to 4 times, so the surface doesn't go to 4 times, so you actually end up with more water on the top. And generally, we don't really know how much water a planet should have, and Earth, even though we see a lot of ocean, is extremely dry. So, there's just a chance that the bigger the planet gets, the easier it is it holds on to lighter elements like water, and so the more water it could have. Does this?
Earth is extremely dry compared to what?
In terms of mass percent. If you just check how much percentage in mass of the Earth you have, it's a very small number of water compared to anything else.
Okay, thank you. Along the same lines, is there any reason to think that these planets on the interior of the habitable zone, like Kepler-69c, would have an atmosphere like Venus as opposed to Earth? Is there any reason to be that pessimistic, or should we be optimistic?
Bill or Tom?
Well, certainly, if you have a planet that hot, that big, and as massive as you might expect, you would certainly expect a lot of CO2 to become from the rocks into the atmosphere. And so you might have an atmosphere that thick, that big, and making the planet even hotter than it would be if it didn't have that atmosphere. Atmospheres usually make the planet hotter, certainly never make it colder.
Wait, I thought, sorry, follow-up question. I thought that sometimes an atmosphere can make it colder if there's enough clouds. Wasn't that what?
So
Yeah.
maybe what you have is colder compared to us, right? We have a certain amount of clouds, and if you don't make more for E, then it would become pretty hot and muggy. But if you make a little more clouds because you have much more water vapor in the atmosphere, we should be fine. And generally what, as Bill was saying, we have Venus. And we have models that say if Venus is like the Earth in the beginning, but you move it, well, if you move the Earth in towards Venus's position, then because it's so hot, as Bill said, you will start to evaporate all of your water, and then you can't get rid of the CO2 anymore. It will build up, so it gets hotter and hotter and hotter, and you end up with Venus. And as Bill just stated, if the gravity or the mass of this thing is even bigger, right, it might hold on to more of that or get more of the CO2, so it can be even worse. This is based on modeling. What we usually do for this outer line of the habitable zone that I showed you, we just have a look in our solar system and we say, okay, Venus isn't habitable. So if you get so much radiation from your stars, Venus, it's probably too much. And then on the outside, we take Mars and say, okay, if Mars were bigger, it would be better because it could hold on to greenhouse gases, but that's roughly from the data where we take the real limits of the habitable zone. Does this?
Yeah, that answers the question. If I have time to ask one more?
Okay, we'll give you one more, Adam.
Thank you, yeah. So there are these two definitions of the habitable zone. Can one of you speak a little bit more about what the difference is between them?
I'll give that one a try. Basically, we have two ways of estimating what the habitable zone is. One is to look at our own solar system. As Elisa has pointed out, if you got out as far as Venus, we believe it would be just too hot to hold that water. If you get out beyond Mars, again, too cold, so the oceans might be frozen. And we call that the empirical habitable zone. But people like Lisa and several other groups are trying to build models of how the atmosphere affects it, how thick the atmosphere is, what the composition would be, and what cloud cover would do. And so they calculate an inner zone that's a little bit tighter than the other one, that they say this is the best place where you'd expect to have water on the surface. So we have two ways of estimating it, and she's described both of those for you.
And so maybe basically just as a small comment, and Bill did this exactly perfect. We don't know how in these models to include what cloud's going to do. And so therefore, it's too narrow, because when it gets hot, you should get more clouds. On the inside, they actually have water clouds, so they cool you. On the outside, they're CO2 clouds, so they warm you, different kind of things. But it's very hard to model these things. So we know that the narrow habitable zone, as Bill said, misses this crucial factor, so it's too small. But we know that within this one, even our existing models, we can make it work.
Great. All right, let's take our attention to the phones and ask a question out there, and then we'll come back to the room here. I'll turn it over to the operator to turn it over to the media to ask questions on the phone bridge.
Thank you. We have a question from Seth Bornstein, Associated Press. Your line is open.
Yes, thank you for doing this. I guess this would be for Lisa or Bill. In terms of the difference between E and F, sort of the rockiness versus the water worldness, one does in general the thought that more watery is more conducive to the beginning and evolution of life, or is it more rocky? I mean, and just a sense. I know we have no idea what any kind of life could develop on here, but a sense of what kind of life since this is potentially very habitable, what kind of life could are we talking about when we're talking about the potential for life, and what differences would the two planets make between each other?
Mr. Baruki?
Okay, I'll try to answer that. If we look at our own ocean, it is just absolutely full of life. We think, in fact, life might have begun there, in the ocean vents and places like that, where chemicals like hydrogen sulfide come out, things that are poisonous to us. So, and the variety of life is absolutely unbelievable if you look at our own oceans. So speculating as to what those oceans would be like is a puzzle. But one of the things that's important is to get rocky material, minerals, elements into that water. And some of the work that Lisa and her group have done, and we'll be talking about, I believe in another press release, is that there is a way of getting the rocky material from the core into the ocean, so there is the chemicals that are required to build life. Clearly, life that builds radio telescopes and communicates with us, or has optical telescopes, it's probably much less likely on a water world unless there is some land. Whereas with a rocky world, it might very well be quite similar to the Earth in almost every way other than gravity would be higher. It would be more, we might not have gotten off of 4 legs to have 2 legs and some arms, simply because that gravity is higher, but we could walk on that. It would just be a little bit more difficult. So it seems to me both of those planets have a real chance of habitability, but we really don't know what life requires to get started, so we don't know whether they have any life.
So I completely agree with Bill. One of the other things that would also be interesting in terms of, somebody asked me, what about if you fly there? As we said, the outer one, as in the models of the habitable zone, will have to build up a lot of CO2 greenhouse gases to stay warm. So if you land on the other one, don't take off your spacesuit, because it's not very good for us to breathe more than 1 bar or like a lot of CO2. We'll have to get some masks to do that. While the other one potentially is going to be very hot and muggy, but doesn't need that kind of CO2. Again, we don't know how these worlds could at all develop, but if you want to write a science fiction story and you land on both, at least we're sure that on F you don't want to take your mask thingy off.
The other thing that Lisa's mentioned along this line I think was rather interesting. If you've got a planet with a massive atmosphere, an ocean planet, we know that, at least in our ocean, we have flying fish. And they fly to get away from predators. So we might find that, in fact, they have evolved birds on this ocean planet.
All right, let's move to the next question on the phone.
Our next question comes from David Perlman, San Francisco Chronicle. Your line is open.
Oh, hi, thank you. My question really is for Dr. Barkley and 67 and 69C. First of all, has that been published anywhere yet? And second of all, could you go a little more, repeat a little bit more about why 69C might be a good candidate for habitability?
Yes, so the paper was published in the Astrophysical Journal today, I believe at 11 a.m. this morning Pacific time. Kepler-69 is certainly on the inner edge of what we've considered to be the habitable zone by the project. The studies of what the habitable zone is are ongoing, and I think one of the most exciting things is this is no longer an academic theoretical exercise, because we are finding planets that really fit into these models, can really test our new understandings of what's going on. I think it's very exciting. There is probably, this planet is closer to a Venus than an Earth, but we're not sure. It has an orbital period between Venus and Earth. It's longer than Venus, and it's around a cooler star, slightly, but still very similar to the Sun. So the answer is we're not sure yet. One of the most exciting things from these discoveries, I think, is the fact that we are finding these small planets on these longer orbital periods. So we're pushing towards the habitable zone, suggesting that there are many small bodies within the habitable zones of their host stars.
I think
May I follow up with one question?
Can I just make one comment to that? As Tom pointed out, and I think that's a very good point, it's like what we know from our solar system and from our atmospheric modeling. If you could also say maybe Venus is a fluke, maybe other planets could somehow have survived more radiation than Venus, and that's what Tom is pointing out. So maybe, and especially with future telescopes, when we find such planets around close stars, so TESS is going to give us targets, and then JWST hopefully can have a look at that. We can test that. We can see if there is an option that if you get more flux than Venus, you can still be a habitable world. Right now we don't know of one, but we can't 100% exclude it either.
Dave, you had a follow-up?
Yes, I did. Just a quick one. Which candidate for habitable zones are you people agreeing on? And is there a big difference in your attitude toward habitable zones? There isn't one standard. How do you determine that? Which kind of habitable zone you're talking about?
Bill or Tom?
in the case.
Yeah, so basically, as Bill was explaining before, we do agree. So this is one of the exciting things in science now. We're working on the models, but we do agree because the basics, we actually talk to each other and we figure out how our different models work, and we make independent analysis, and we agree on the limits of the habitable zone that we use. And so Bill explained it very eloquently how we do this. So in the narrow habitable zone that we have in our paper, and that we also show in the science paper, in Bill's science paper, is where we take the Earth, and as I said, we don't have a feedback for cloud, but other than that, we know how the Earth would evolve if you put it closer to the sun and further away from the sun, getting really hot, getting really cold. And the other zone, because we know that we're missing cloud feedback in this model that we use for the narrow habitable zone, is empirically looking at Mars and Venus in our own system and determining it there. So there is no conflict at all about where the habitable zone is. You know, we might say, okay, now we found something new, and so we can stretch it out a little bit. But the empirical habitable zone from the data in our solar system basically tells us that Venus is not habitable, and so that's what we take for data-based habitable zone. So what Tom was saying is just that there's an error bar in where the planet actually is, or how hot the star really is. So there's an error bar in how much of the flux, how much of the radiation energy from its star that planet 69c gets. And if you have a look at one of the first of my slides, or one of them, you see this habitable zone, and for Kepler-96c, you see this error bar. 69c, not 96, sorry, 69c. You see this error bar, and you know, part of the error bar gets into the habitable zone. So with new measurements, we figure out the star is actually cooler, radiates less, then we shift it into the habitable zone, right?
And Tom or Bill, did you have a quick follow-up to that? Okay.
Well, I think that Lisa's pointed out that the wider zone is based on our own solar system, and that these systems are different, and that they might very well have an empirical, we may very well find the empirical habitable zone is wider than we have found. And so we do need to look at that data. And so I think that Tom's quite right. This is something that we consider in the habitable zone, or so close that we consider it a habitable zone, basically.
Okay. We're coming up on the top of the hour already, so we have a few more questions, or we have a number of questions from social media. So let's try to get through a few more, and if we could answer questions a little more briefly, that way we can get to more questions. So let's go back here in the room. We had a question in the front.
Yeah, hi. My name is Mike Stager. I'm with 21st Century Science and Technology. I just want to first just applaud what you've done to keep people inspired regarding space exploration, especially under these austere budgetary conditions. I'm glad you guys could all make it here today. Two questions. One a bit more future-oriented. We mentioned TESS. I'd like to know a little bit more about where we can go, and especially if we were able to expand the budget, what do we see as possible, not so much restricted, but what's actually available technologically to really look at these questions. And then second, because we've found over the last few decades, life is far more formidable than we had maybe previously considered. Under what considerations do we have in looking at the organization of the star system, in terms of planetary arrangements, how that might affect the characteristics, and in that context, what was recently announced a few months ago, the asteroid belts, how these are found to be consistent in some of the project's research. So there's just two questions, if those could be addressed.
Let me answer the first question. Basically, you're saying, what could we do if we had more money?
Yeah.
And it's almost limitless. The objective of what we're trying to do is to explore the galaxy looking for life. Kepler is this one first step. TESS is another step. But the next big step is likely to be something like what people were talking about years previous, the terrestrial planet finder. What we're trying to do there is to look at the atmospheres of these planets and find out, are they CO2, is there water? With those two things, you can have life. Those are what plants need. If you have oxygen, maybe they're higher animals as well. If they're freons, you've got it made. Obviously, intelligent life is there. So we want to look at the composition of these atmospheres, and that's going to take a much more expensive, extensive mission. But we've talked about it, we've planned it. once we get the funds in the future, I think we'll see rapid progress in that direction because we have several different methods of approaching that. In fact, the National Academy of Sciences have said that when we get the numbers for Kepler, we know how frequent Earth and habitable zone are. If they're very frequent, just look at the nearest stars. If they're infrequent, then you have to look much further out into the galaxy. So you build a much bigger, more powerful instrument, but a much, much more expensive one. So we're looking forward to getting these frequencies of planets as a function of size and habitable zone and so on. But I think that's what we're going to see in the future, is the movement toward a better understanding of these planets and whether they might have life. But even if you found that, if you found an atmosphere like that with water and CO2 and oxygen, that's not a proof there's life. You'll have to have missions beyond that that will help us understand, is there actually life there? So we've got ways of using your money through our children and grandchildren, so lots of plans.
And maybe if I can touch on the other thing you talked about the asteroids and life being very versatile. One of the things that I also want to point out is this habitable zone is defined as where we can have liquid water on the surface of a planet or a moon, if you want. If you freeze the surface of the planet over, it's not to say that you couldn't have an ocean below where you could have life. But if you can't go there, this is our whole discussion of going to Europa, like basically drilling through the ice and having a look. If you take Europa or something bigger than Europa, right, with a huge ice layer, put it 10 light years away, it's not easier to detect if there's life, right? And so this habitable zone, in a way, we define it for liquid water so that whatever life produces has an easy chance to get in the atmosphere, and so we don't have to fly there. We can build bigger telescopes, as Bill just said, to pick up the signatures of life from the atmosphere. Because I think we're not talking, even if you give us loads of money, actually flying to 1,200 light years things or planets very far away will require some really, really good engineers. And so if anybody has a smart idea how we can travel faster than light, please let us know.
Great. Okay, let's go back to the phones. Operator?
We have a question from David Templeton, Pittsburgh Post-Gazette. Your line is open.
Yes, if Kepler were looking at our solar system, would Earth be in that narrow zone and Mars be kind of on the edge or beyond the narrow zone, or what would it conclude about our solar system?
Well, the first thing, of course, is because Kepler's has been analyzed data for only the first about 2 years, we would not have seen 3 transits of any planet in the habitable zone, and certainly that goes for Earth, and certainly that goes for Mars. So we wouldn't have seen anything yet. We have to look longer. We have to look at the data that we have stored. But if we postulate that we've looked longer, we would expect to find those planets, certainly 62F, in the narrow habitable zone. I don't know about 62E. Lisa?
So basically, what you have, and it's a good point about in our own solar system, both Earth and Mars fall in this narrow habitable zone, but Mars is just too small. It doesn't hold on to an atmosphere like the Earth does, so it cannot build up greenhouse gases that could keep it warm at that radiation, because it gets less radiation, less energy from its star than our own planet. So the habitable zone is defined for an Earth or something bigger than an Earth, and you keep moving it closer to the star, further out from the star, and figure out where it actually stops. So it gets frozen on the outside and loses all its water on the inside. That's how we define it. And so for E and F, bringing it back to the Kepler-62 system, this really narrow definition of the narrow habitable zone where we don't have any cloud feedback. Again, I said clouds warm or cool, depending which ones they are. F is in it. It needs to build up lots of CO2 to actually stay warm, like as if you put the Earth at the Mars position. And E is just in this wider habitable zone because it will actually need to have more clouds to be nice and warm.
Thank you.
Our next question comes from Eileen Klotz, Reuters. Your line is now open.
Hi, thanks very much. I just had a quick question about the the growing list of exoplanets. On exoplanets nasa.org, I didn't see any of these new candidates on there, and the total on that site had 697. Is that accurate, and is it reasonable just to add these 3 or these, let's see, 5, or the total number, including the ones in the habitable zone, to that list?
So we're announcing 7 new planets today, 5 around Kepler-62 and 2 around Kepler-69. And these are confirmed planets, so they will be, I presume, added to the list as soon as possible. These results have only come out at 11 a.m. today, so I think they haven't updated just yet.
Thanks.
Nancy Atkinson, Universe Today, your line is open.
Can you talk a bit more about how important these planets' atmospheres are to make them habitable? And then you did talk a little bit about the terrestrial planet finder and that kind of mission, but what kind of mission or telescope do we need to find out more about the atmospheres of distant exoplanets?
Measuring these atmospheres is a great step forward in technology. It really requires that's the edge of what we might be able to do. You need a big telescope. You need to have a telescope that blocks out the light of the star, because it's over 1 billion times brighter than that of a planet. That's extremely difficult to do, to the point where you've blocked it out so thoroughly that you can actually see the planet. But once you can do that, then you can actually do spectra and get the composition of the atmosphere. When people were developing the concepts and the engineering ideas for the terrestrial planet finder, they felt they might be able to go out something like 30 light years, maybe 100 light years, not as far as the planets we're discovering today. I think what will help them and help a JWST to look at some planets is TESS. TESS will go and look through the entire sky and find those stars with planets that are closer and nearby. In many ways, Kepler was a scout. It scouted deep into the galaxy to find out what the frequencies were, and to show there were a lot of planets to find. It's accomplished that. And now these new missions will come online and give us more information about these planets, but the big step is that step where we first start measuring the composition of the atmospheres, and that will be a very technologically difficult task.
Okay, Irene, just to follow up to your question about the number of confirmed planets, you can go out to the NASA Exoplanet Archive, and that's exoplanetarchive.ipac.caltech.edu. And you'll also be able to access all of the Kepler missions data that has the light curves and everything, and you'll have the confirmed planet count there. So these planets will be added to that. So let's go to social media then, now that we've wrapped up our calls on we do have one more question from the phone.
From Cesar Bema, O Globo newspaper. Your line is open.
Yes, thank you. I would like to know what would it take to verify these the 2 new planets in 69 E and F are indeed rocky planets, or are they too far away that our technology, our current capabilities can't confirm us that?
Let me answer that one. Basically, we want to know the mass of the planet as well as its size. That gives you the density. If the density is like the Earth, 5.7, or it's like 10b, which is over 8.8, then we're pretty sure it's rocky. The difficulty is that when a planet's in the habitable zone, it's so far from its star. It's moving very slowly. These planets are small, and they're fairly light compared to the giants that we've been looking at. Consequently, the radial velocity method, the Doppler method, where you're looking at the wobble of the star, doesn't have the precision required. It can't make that measurement. We have a second way of getting at masses, and that is if there's 2 planets in orbit, they tend to affect one another. They tend to slow the outer planet down for a while, and it speeds up. So the orbital period changes in a rather regular way. It gets a little bit longer, gets a little bit shorter, gets a little bit longer, and by the amount that it gets longer and shorter, in the distance from that other planet, you can get at the mass of these planets. And we have found and determined masses that way. But we have not found any planets in 62 or 69 that are close enough to affect the planets we're talking about. That may happen, in the years coming, but right now we don't see the variation that's needed to get these masses. So right now we have no method of getting measurements of the mass. We can only use our theory and to surmise it from what we've learned about other planets which are closer to their stars.
Well, let's take our first question from social media. Where are you able to detect solar-like oscillations in Kepler-62, the star, to pin down its parameters?
The stars, most stars have some variability. They have storms like the sun, and that produces acoustic waves that pass through them. That oscillation, that vibration, can tell you about the interior of a star. It can tell you about the size of the star with very high accuracy. It can give you some idea of the chemicals there. But to do that, you need an enormous amount of light over a fairly long period of time. Our telescope is big enough to do that for many other stars, but not for Kepler-62. For Kepler-62, it's just simply too dim. Now, Kepler-69, that's bright enough, isn't it?
Unfortunately, for sun-like stars, we can detect these solar-like oscillations and use that to derive very accurate stellar properties. Unfortunately, Kepler-69 was also too faint to be able to detect these oscillations. So we had to measure the stellar properties, the stellar mass and radius, via spectra, which is very good but less accurate.
Okay, let's take another question from social media. How will the habitable zone change throughout a star's life cycle?
So that's a very good question, because that's what we're trying to learn for the future. But generally, if you just think about it, initially, the star is colder. And so the sun was, for example, 30% less luminous. We got 30% less energy when it was really young, when it just started out. And now it's just brightening with time. And so basically, it gets hotter and hotter with time. But this habitable zone is actually defined for a planet that can deal with that, meaning that if it gets hotter, it washes out the greenhouse gases like CO2 very efficiently from its atmosphere, while if it gets colder, it freezes the surface over, and so it builds up CO2 in the atmosphere until it's warm again. And that's basically similar to what happened, if you want to think about it, during the Earth's lifetime. In the beginning it was colder, we had more CO2, more greenhouse gases to keep us warm. But if you now go really far in the future, let's say a second lifetime of us, so we're about 4.5 billion years old, then at one point the planet actually stops being able to cope with that, because you get so much radiation that you start to evaporate the oceans. But that's a really long time from now. So the habitable zone concept and the lines that we showed you are good for a couple of billion years, and still for a couple of billion years to come.
Let's take one last question from social media. How does the discovery of the Earth-like planets like Kepler-69s and Kepler-62s help us understand our own world? Tom, you want to take that?
First, I'd like to make it clear that we wouldn't describe these as Earth-like planets. These planets are larger than the Earth. We call them super-Earths. We're still progressing towards finding the first truly Earth-like planets. That's where we'll probably be in a few years when we find these, if they exist. And we simply don't know whether other Earth-like planets are out there yet. We haven't found any. Lisa, do you want to go ahead?
I agree with Tom, but let me take the little more positive view from a planetary modeler. Because if you have a rock, and that rock behaves similar like the rock we live on, then we think we can learn a lot from once we get the atmosphere and look at it, the spectral fingerprint, because it will just tell us how an Earth a bit bigger, a bit smaller, actually works. And so yes, I would like to find the exact Earth analog. I keep calling these planets Earth-like because yes, they're bigger, they're super, and somebody once asked me, is it like better to live there? I don't think so, but we called them super Earths and now we stuck with it. But the super Earths and mini Earths, if you want, it's just a bit smaller, actually should function, and again, we don't know that, but they should function from everything we know, similar to the Earth, down to a size where they're not geologically active anymore. They cool out faster and thus cannot recycle greenhouse gases like Mars did. But I think these discoveries are actually informing us, and we're learning about our own world with every step, with every model that we do.
Great.
The other thing it's telling us, of course, is these discoveries show that other planetary systems can be very different from our own, and yet might well be habitable. So that's new knowledge for people to try to understand when we're thinking about how did our solar system form? Other solar systems have planets in the habitable zone. How did ours form?
Great. Thank you very much. Thanks, panelists. That concludes today's news briefing. To learn more about NASA's Kepler mission, visit us on the web at www.nasa.gov/Kepler. And you can also join us on social media. And you can go to Twitter, twitter.com/NASA Kepler, and join us on Facebook as well at www.facebook.com/NASA's Kepler mission. Thank you all for joining, and clear skies to you.